All right, last couple of times we took a look at sequences. Remember, sequences were just lists of numbers. This time we're going to take a look at series. So this would work well if I actually had a piece of paper and a camera and I could show you, but let's try to do the best we can with a drawing like this. So suppose I have a sheet of paper, right? My sheet of paper looks like this, and I decided to take that sheet of paper and cut it in half. Right? So now I've got a half a sheet of paper here and a half a sheet of paper somewhere else. So this is half of the original sheet of paper. Now, I'm looking at this half that's cut out, and I'm going to take half of that half. So if I take half of a half, now I got a quarter. So a quarter of the sheet is there, that quarter of the sheet is not there. All right, so now I'm going to take the quarter of the sheet that's not there, and I'm going to cut that in half. All right, so if I got a quarter of a quarter, now that represents an eighth of the original. So what I'm doing is I'm starting to build back that sheet of paper, right? I got a half, I got a quarter, I got an eighth. If that eighth is there, that's the eighth that's missing. Cut the eighth in half, now I got a 16th. All right, so that's a 16th, and this remaining piece over here is also a 16th. All right, cut that in half, and we're starting to get at the point where I can't draw that small bit anymore. All right, that's a 32nd. And that piece is also a 32nd. So if you start looking at the pieces of paper that I'm adding together, the first was a half, and then next to that half, I joined it with a quarter, and then I joined an eighth, and then I added a 16th to it, and then I added a 32nd to it. And I can keep going on this. I can keep going forever, and you notice that I'll end up with an infinite number of terms in my series. However, I will never end up with more than the one sheet of paper that I started with. So what I've created here is what we call an infinite series. The first term is a half, the next term is a fourth, the next term is an eighth, the next term is a 16th. In general, I can look in infinite series like this. All right, so for my infinite series, I'll take the first term, and I'll take the second term, and I'll take the third term. And you notice this time I'm putting plus signs between them. And I'll take the nth term, but then I'm going to keep going. This infinite series I can write as a sum. I can write it as the sum from k equals 1 to infinity of all the a sub k's. Or sometimes we use n's, right? The sum from n equals 1 to infinity of all the a sub n's. That is my infinite series. Now, if you look at this series that I made here with this square and this sheet of paper that I was cutting apart, the first time I did that, I didn't have the whole series, right? The first time I did it, I had only one piece of the series. That's going to lead us to a little discussion of what we call partial sums. And so if you look at the first partial sum, the first partial sum was just the 1/2. Then the next time I did it, I added the half plus the quarter. And so I had 3/4. The next time, I added the half plus the quarter. I also added an eighth. So I had a half, I had a quarter, I had an eighth. Add those three things up, I had 7/8. The next time I added up a half and a quarter and an eighth and a 16th. So I'm looking at just parts of these sums. That's why they're called partial sums. So if I add those together, I get 15 out of 16. Now, be careful of the terminology. We're talking about an infinite series. We're adding all the terms together, but I'm not looking at the whole thing. I'm just looking at part of it. So I'm looking at the first term. I'm looking at the first and the second term. I'm looking at the first, the second, and the third term as what we call partial sums. Now, from these partial sums, let's make a sequence of partial sums. And my question is, does this sequence approach a limit? So here's my sequence of partial sums. 1/2, 3/4, 7/8, 15/16. You might imagine the next one is going to be 31 32nds, 63 64ths, and so forth. Does this partial sum sequence approach a limit? So what is the limit as n approaches infinity of the nth partial sum, right? This thing here is what I'm going to refer to as the nth partial sum. Can you tell what it is? Well, we only started with one square, or one sheet of paper. So these partial sums look like they're approaching 1. If that is the case, if that limit is finite, then the series converges. So if the sequence of partial sums has a finite limit, right? So if the limit as n approaches infinity of the nth partial sum is some finite value, then the series converges. Remember, the series is the thing with that summation notation, the sum from k equals 1 to infinity of all the a sub k's. That series converges. Okay, there's that word converge again. We talked about whether sequences converged. A couple of chapters ago, we talked about whether integrals converge. Now I'm interested in whether series converge. So I take my series, I write out the first few terms, I look at the partial sums where I add the first plus the second plus the third. If that sequence of partial sums approaches a limit, then that series converges. So in this case, my series converges, right? It converges to that one original square that I started with. It'll never be more. It will eventually approach that entire square. All right, let's take a look at a couple of other cases. Okay, not all of them are apparent right away. So let's say I have this series here. I've got a series, the sum from n equals 1 to infinity of all the a sub n's, where a sub n is equal to 1. Well, that's pretty easy, right? The first term is 1, the second term is 1, the third term is 1, the fourth term is 1, the fifth term is 1, etc. So let's look at the first partial sum. The first partial sum is just 1, okay? The second partial sum is the first term plus the second term, which is 2. The third partial sum is the first term plus the second term plus the third term, which is 3. The fourth partial sum is the first plus the second plus the third plus the fourth, which is 4. So now let's look at the sequence of partial sums. Okay, so the sequence of partial sums is 1, 2, 3, 4. What does this do? If I take the limit as n approaches infinity of the nth partial sum, I'm not going to get a value, right? I'm going to get infinity. This thing just keeps growing and growing and growing. So the series diverges. Is not doing anything crazy, right? It's just a series of ones, 1 plus 1 plus 1 plus 1 plus 1. But yet, that sequence of partial sums does not approach a limit. Therefore, that series diverges. So it doesn't have to be doing anything crazy just to get it to diverge. All right, let's look at another case. All right, here's another case. Again, this one's not doing anything crazy. Let's say that my series was just alternating ones. So I have 1 minus 1 plus 1 minus 1 plus 1, etc. Does this thing converge? Well, you might go, all right, I'll take the first two, and the first two become a 0, the second two become a 0, and so if I add 0 plus 0 plus 0, sure, the whole thing converges. But that's not how it works. Let's look at the partial sums. First partial sum is 1. The second partial sum is 1 minus 1, which is 0. The third partial sum is 1 minus 1 plus 1, which is 1. The fourth partial sum is 1 minus 1 plus 1 minus 1, which is 0. So if I look at the sequence of partial sums, it goes 1, 0, 1, 0, etc. What is that approaching? It's not approaching a limit. It's not doing anything crazy, right? It's not becoming infinite, but it's also not approaching a limit. Therefore, that thing diverges also. So even though it's not doing anything wild, it still diverges. All right. Let's take a look at a series again that looks like this. So let's look at the sum from n equals 0 to infinity of 1/2 to the n. All right, so let's write out the first few terms of this series. I start with 1/2 to the 0 power. 1/2 to the 0 power is 1. 1/2 to the first power is a half. 1/2 to the second power is a quarter. Half to the third power is an eighth. half to the 4th power is a 16th, half to the 5th power is a 32nd, and by now I think you get the idea where this is going. All right, if I add all these pieces together, what is the sum? I mean, does this converge or does it not converge? Well, you realize that this piece here was the series above the converged to 1, right? That was the original piece of paper. So if I take that 1 plus the 1 that's there, you would think that this whole thing adds up to 2. And that's true, but do I have a better method than just eyeballing it? Well, this series happens to be a special type of series. This one is called a geometric series. Remember we talked about geometric sequences that had a constant ratio? This thing is a geometric series because it has a constant ratio. If you remember anything about geometric series, if you've seen them before, in this case, the ratio of my geometric series is a half because I keep taking each term, multiplying it by a half to get the next term. If that absolute value of the ratio is less than 1, then the geometric series automatically converges. So it could be an alternating one, right? It could have a ratio of -1/2. It could have gone 1 minus a half plus a quarter minus an eighth plus a 16th minus a 32nd. And in that case, that series would converge as well because the absolute value of the ratio is less than 1. If that's the case, then there is actually a formula that tells us how this thing converges. And the way it converges is like this. It converges to a over 1 minus r, where a is the first term. So we have some idea what this is going to do, right? This is going to converge to 2, at least we think it is. So in our example up there, the first term is 1. The ratio is a half. Let's see if that works. First term is 1. Ratio is a half. So if I do a over 1 minus r, I get 1 over, if I take a half away from 1, I get a half. Well, 1 divided by a half is 2. So this is the sum of that series. And that also tells me that the series converges. And if I look at the sequence of partial sums, it would go what? 1, 1 and a half, 1 and 3/4, 1 and 7/8, 1 and 15/16, 1 and 31/32. Eventually that series would begin to converge, and it would converge to 2. If that constant ratio is bigger than 1, right? So what happens if that r value is bigger than 1? Right, we could take a look at a case. We've actually seen a case like that already, but let's try it again. What if the absolute value of r is bigger than 1? So let's say I had the sum from n equals 0 to infinity of 2 to the n. So I would end up with 2 to the 0, which is 1, plus 2, plus 4, plus 8, plus 16. And you can tell that as you take these partial sums, the first partial sum will be 1. The second partial sum will be 1 plus 2, which is 3. 3 plus 4 is 7. 7 plus 8 is 15. This thing diverges. It turns out that you can write a geometric series as a sum in this way. So suppose I went back to my example of the 1/2 to the 0, 1/2 to the first, 1/2 to the second, etc. Could I write it like this? 1 plus 1 times a half plus 1 times a half squared plus 1 times a half to the third, and so forth? Sure, I could. This would be AR to the 0 power. This would be AR to the first. This would be AR to the second, AR to the third, and so forth. Hang on to that thought, because eventually we're going to come back and take a look at it. I could sum it up like this. The sum from n equals 1 to infinity of a times r to the n minus 1. As you're working through these series problems, pay attention to what we call the indexes. The indexes, or indices, I guess I should say, there's a plural, are these numbers on the top and bottom. Well, if this is an infinite series, then the top one's going to be infinity. But this bottom one tells me where to start. A couple of them we started at 0. This one I started at 1. It makes a difference. If I start at the wrong spot, I'm going to end up with the wrong number of terms. And I may end up with a different sum because that first term will be different. All right, what can I use these nice geometric sequences and series for? Suppose I had a repeating decimal. Okay, so let's take a look at repeating decimals. Suppose I had 1.272727 and it just kept going repeating like that. I guess I could simplify it and write this as 1.27 repeating. Right? Draw the bar over that 27. That means that it just keeps repeating 272727. All right. How can I write this as a geometric series? Well, I could write this as 1. The first two decimal places are out of 100, so 27 out of 100. The next two decimal places are out of 10 to the 4th, right? So 10,000. The next 7 is really over 10 to the 6th. The next 7 is over 10 to the 8th, and this will continue on and on and on. So let's pull the 1 on the outside here. And then what I'm going to do is I'm going to factor out a 27 over 100 out of that entire piece that remains. So when I factor a 27 out of 100 over the first term, I get a 1. Factor a 27 out of 100 there, and I get 1 over 100. Factor a 27 over 100 out of that third term, and I get 1 over 10 to the 4th. I get 1 over 10 to the 6th, and this keeps going on. You realize that what's in the middle now is a geometric series. It's the sum from n equals 0 to infinity of 1 over 100 to the n. Right? Because 1 over 100 to the 0 power is 1. 1 over 100 to the first power, there's 1 over 100 to the second power, right? 100 times 100 is the same thing as 10 to the 4th. This thing that's in blue converges, right? It's a geometric series that converges to a over 1 minus r, and I know that because the ratio is 1 over 100, and 1 over 100 is clearly less than 1. Okay, so the first term is 1. The constant ratio is 1 over 100, so that gives me 1 over 99 hundredths, which is 100 over 99. So everything that's in that green bracket here, everything that's in here adds up to 100 over 99. Great. Then let's move this forward. How did my division sign get moved? There we go. Let's bring it back where it belongs. So I get 1 plus 27 over 100 times, well, we said that piece that was in blue is really 100 over 99. So now I can play around with this a little bit, right? I can cancel out those hundreds top and bottom. 27 over 99 simplifies, so I get 1 plus, take a 9 out of it, I get a 3 over 11. Let's make ourselves a common denominator. 11 out of 11 plus 3 out of 11 gives me 14 over 11. So I've written that repeating decimal now as a rational number, meaning that that repeating decimal, 1.2727, even though it was clearly not terminating, it was still a rational number because I can write it as a over b, where a and b are both integers. So hold on a minute. Does that mean that I can try another one? Here, let's try another one. What if I started with 0.9 repeating? Okay, so let's take a look at 0.9 repeating. 0.9 repeating is boring, right? It's just of length 1. So that means I can write this as 9 tenths. The next one would be 9 hundredths. The next decimal would be 9 thousandths, right? Because think about what you have after the point. You got a tenth place, you got a hundred place, you got a thousandths place, you got a 10 thousandths place, and you've got a 100 thousandths place. Okay. Do the same thing we did before. Factor out that 9 tenths, and I'm left with 1 plus 1 over 10 plus 1 over 10 squared plus 1 over 10 to the third, and that thing just keeps going, right? Well, that thing on the inside here is a geometric series. it converges to a over 1 minus r, so 1 over 1 minus a tenth, which is 1 over 9 tenths, which is 10 ninths. And now suddenly a funny thing happens, right? We have a 9 tenths over here. We said that that geometric series converged to 10 ninths. And when you multiply those things together, you get 1. So is 0.9 repeating the same thing as 1? Absolutely. 0.9 repeating is the same thing as 1. You keep adding more decimals to it, and that distance between the 0.9 repeating and 1 becomes nothing. So it is the same value, right? That 0.9 repeating always has more nines just because you think you're stopping at 3 places. No, there's actually more and more and more. And there's no number between 0.9 repeating and 1. It is the same thing. I mean, I guess another way to look at it is if 0.3 repeating is a third, take 3.3 repeatings and you get a 0.9 repeating. Take 3/3 and you get 1. All right, we'll take a look at a couple of examples of these in the second part of 10.3.